Hi, this is Livia Seitz from the German Cancer Research Center. Surgical scene segmentation is an important prerequisite for autonomous robotic surgery. The topic has gained great attention during the past years, with several thousand publications occurring every year. In our previous work, we achieved surgical scene segmentation that is on par with human expert performance. So are these algorithms now ready for clinical application? Well, actually, they aren't. A problem that has not yet been addressed is the presence of geometric domain shifts. Such domain shifts are common in real-world surgeries due to variations in the surgical procedures performed, or for example due to situs occlusions. So how do state-of-the-art segmentation networks perform under such geometric domain shifts? Remember our strong baseline performance with a DICE score of 0.9 on in-distribution data. Upon encountering geometric domain shifts such as organs in isolations, missing organs, or for example occlusions, large performance drops can be observed for state-of-the-art segmentation networks. The results shown here are based on hyperspectral imaging data. We actually had a look at both RGB and hyperspectral imaging data and were quite surprised to see those large performance drops also for hyperspectral imaging data, despite the much larger spectral information content. So how can we solve this problem? In our previous work, we showed that image-based surgical scene segmentation largely outperforms patch-based and image-based segmentation models. However, those small spatial granularity models actually would be more robust towards geometric out-of-distribution, since they just look at a much smaller spatial context. So why not combining the best of all models through a multi-scale learning approach? Well, actually we tried, but found no improvement in performance. Furthermore, increasing the network complexity comes with additional disadvantages, like having to learn more parameters, longer training times, and higher GPU memory requirements. So we went for a much simpler yet effective approach, which is a targeted data augmentation. First, we analyzed 35 representative works in the field of surgical tissue and instrument segmentation. And we found that actually most of them rely on very simple data augmentations, such as affine or perspective transformations and kernel transformations like Gaussian blur. So we came up with a new yet simple augmentation scheme that we refer to as organ transplantation. The idea is to place an organ into an unusual context, while maintaining both the shape and the texture. This is achieved by transplanting all pixels belonging to one object class into a different surgical scene. And at the same time, we transplant the segmentation mask accordingly. We compared our method against topology-altering transformations that we have been proposed for image classification and for object detection, namely elastic transformation, hide and seek, random erasing, jigsaw, and cut mix. We investigated 3 common out-of-distribution scenarios, like organs in isolation, where, for example, large parts of surgical scenes are covered by abdominal linen. We had a look at resected organs, and we had a look at occlusions, for example, from the surgeon's hands. So in total, we had a look at 6 out-of-distribution test data sets, comprising 600 images from 33 pics, annotated with 19 classes. While large performance drops could be observed for the baseline, which relies only on very simple data augmentation methods that are common in the surgical scene segmentation community, our augmentation scheme improved the performance by up to 90% on out-of-distribution data. It then yields performance that is on par with in-distribution performance. It outperforms existing topology-altering transformations as well, as you can see in the ranking plot here. So in conclusion, geometric domain shifts, which had so far been overlooked by the community, lead to huge performance drops for state-of-the-art segmentation networks. And this effectively hinders clinical translation, as such geometric domain shifts are very common in real-world surgeries. However, with our novel organ transplantation augmentation, we provide a network-independent and computationally efficient solution. Also, we made our implementation publicly available as part of the Cornea library. So if you want to learn more about our work, please come and visit us at our poster. You can also learn more about the different results obtained for RGB and HSI data, or a detailed augmentation ranking for our different out-of-distribution scenarios, and much more. Finally, we'd like to thank all our clinical collaborators, our colleagues, our funders, and of course you for your attention.